everyone. Let's start today's session. Welcome to day 6 of our DSA bootcamp. We're now reaching closer to the end of our bootcamp. Now, just a few topics are left. After this, we shall be studying about tree traversal, basic sorts, merge sort, and quick sort. And today, we shall also be assigning the HackerRank contest to you. And 23rd March, 11:59 p.m. shall be the deadline for it. So today we shall be studying about heaps and recursion. Heaps might be a new concept for a lot of people, for freshers, and recursion is a concept that we have already studied about in Python. So let's talk about the relevance of heaps and recursion. Heaps are actually a data structure which help us organize data efficiently, and recursion are used to solve problems efficiently. Heaps find their applications in priority queues, where all of the elements are arranged based on their priority. So basically, the element with the highest priority will be assigned the highest number, and based on that, we shall be carrying out various operations on our heaps. And heaps, this priority queues concept is used in job management and task scheduling. And heaps help us to find the most important elements quickly. Heaps are also used in graph algorithms, which is the Dijkstra's algorithm and the Prim's minimum span tree, which we shall be studying about in our discrete mathematical structure course. And recursion is a concept that everybody knows about. In recursion, functions call themselves repeatedly until a base case is reached and our function condition terminates. And recursion is actually a concept that is helpful in divide and conquer algorithms, where we break down our problem into smaller problems. And in recursion, we simply break down our problems into smaller problems, which help us to carry out our operations faster. And they are also used in backtracking algorithms, which is a concept used in AI. And in backtracking algorithms, we basically explore all of the possible solutions one by one until a dead end is encountered. In that case, we start backtracking. So we shall be starting with our heaps. So we shall be carrying out insertion and removal operation on our heaps. And for that, there will be various functions defined. So let's take an introduction of heaps. So in heaps, we shall be initializing a binary tree. Now, you might be thinking, is it the same as the trees that we studied about yesterday? That's actually not the case. So let's just recap what we learned in yesterday's session. We studied about binary search trees and graphs. So a binary search tree and a binary tree is completely different. In a binary search tree, all the elements to the left are lesser than the parent node, and all the elements to the right are greater than the parent node. And binary search tree is called binary search tree because it carries out this binary search technique to find out the element really fast. And a binary tree is simply a tree where the parent node has maximum two children. So that's essentially what our heap is going to be. It's going to be a binary tree. And in heaps, as we are going to use it in priority queues, our heap that is in a max heap, for example, the node that is at the first index shall be having the highest value. And as we go down towards its children, you'll find out that the value keeps decreasing. Every single child has a value that is lesser than its parent. This is the case with a max heap. And if we were having a min heap, then this condition would have been vice versa. The value at index 0 would have been the least value. And one more factor about heaps is that it's supposed to be a complete tree all the way through, which means that there should be no gaps whenever you're filling the tree. We shall be filling the tree from left to right continuously. Now, for example, you could have a heap where, let's just go through the visual firstly. So as you can see, from left to right, we keep on adding the elements. Then we add our 58 node, which is the child of our 72 node. So as you see here, if we simply added 27 as the left side towards 61 node, then our heap would no longer be complete. So this would not be a valid heap. This is a concept to keep in mind. And this concept is very important when implementing various operations on our heaps. So let's bring this back here. We add 55 and now it's a complete tree. So this is essentially what a complete tree means, which means there are no gaps in any of the children. Is that clear until now? This is an example of a minimum tree, what we saw here. All the elements kept increasing in value as you go down towards the tree, as you keep descending from the tree. As you can see, 18 is the root node and it has the least value. Let's carry out operation on max heap. We shall be carrying out operations only on max heap, and I shall be sending pseudocode for max heap and min heap as well. You can implement it for your understanding. As you can see here, if you saw this specific arrangement here, as you can see, 72 is located here, 61 is located here, and 55. You can interchange the value of 55 with 61, and this would still be a valid heap because it still satisfies all the conditions here. As you can see here, 72 is the left side of 99, and 58 and 61 are its children, and they have lesser value than 72. And then we have 55 as the right child of for our 99 node, and 27 and 18 are its children, and they are lesser than our 55 node. It's valid this way and it's valid the other way as well. Now, whenever we're implementing our heaps, we shall be using it using our priority queue. So we shall not be defining any node class for implementing heaps. We shall not be using linked list to implement our heaps data structure. We shall simply use a regular contiguous element list. For implementing heaps, we shall be using a regular list instead of a linked list. And all of the elements will be added into our list starting from index 0 until the length -1 of our list. And just for the sake of explanation, just so that it's easier for you to understand the concept, we shall be taking all of the values and shifting them towards the right so that index 0 is not occupied. Now we shall be talking about children and parents of all of these nodes. As you can see, if we arrange our heap again, we can see this is how it's arranged. Let's pause this and take a look at this. So 99's children are 72 and 61. 72's children are 58 and 55. And now we shall be looking at exactly how all of these elements are arranged in our priority queue. That is our heap. As you can see here, if we want to find out the left child index for our parent node, we shall simply return 2 times the index of our parent here. As you can see, the child of 99 is 72. The index for 99 is 1, and 72 is located at index 2, which is 2 times 1, which is 2 times the parent index. And if we want to find out the right index, it would be 2 times parent index plus 1. As you can see here, 61 is located at 3. And if we have our children given to us already, and if we want to find out our parent node, we shall be saying index -1, floor division 2. You shall see it soon. For example, if you have 27 located at index 6, then you shall simply divide this number by 2 and it shall return 3 to you, as you can see here. And then we can know that the uh, parent is 61, which is located at index 3. We shall simply go to this location 3 and find out that 61 is the parent node. And as I said, we shall be carrying out floor division on our children to find out the parent value. So if we divide this index 7 by 2, we shall get 3.5. And since we are doing floor division, we shall simply return 3. And then we are able to find out that 27 and 18 have 61 as their parent node. If there are any doubts until here, you can unmute yourself or you can send a chat. Yeah, now while I was explaining this concept, we shifted all of our elements to the right and we didn't occupy our index 0. But when we actually implement our method, we shall be starting from index 0. Let us continue. Now we shall be looking at our insertion operation. Let's just take an introduction to it. Just pay careful attention to this concept. So we have our already existing heap here. And for example, if we want to append this 100 value into our heap. Now, after we insert 100 into our heap, you can see that it is no longer satisfying the heap condition, this max heap condition, where the value with the greatest value is not at the first location. So for that, we shall have to bubble up this node to the relevant position so that our heap condition is satisfied. As you can see, for that, we shall have to first compare our node, our current node, with the parent of it. Is this clear until now? Any issues here? If there are any issues, just simply unmute yourself. So we compared 100 with 72 and we swapped their location. And we shall be continuing to carry out this operation until our heap condition is satisfied. So now we have replaced the position of 100 with 72 and we have changed 72 to be the right child of 100 as you can see here. Now again we shall be taking our 100 node and we shall be comparing it with our parent node here which is 99 and we find out that 100 is greater than 99. So we shall be swapping these two. And now our max heap condition is satisfied and our insertion operation is complete. For example, now we'll take another example where we appended 75 into our heap and then we compared it with 61 and then we swapped those two and now we compare 75 with 100 and we find out that 75 is lesser than 100. So our insertion operation would stop here, our code will stop running here. As you can see here, we append 100 and all the time whenever you insert an element into your heap, it shall always be going into the last index of your heap. And then we shall carry out comparison with its parent. So for 5, we shall carry out floor division on it. 5 by 2 will be equal to 2.5. And then as we are carrying out floor division, we will return 2. Now 2 at index 2, we shall find out this 72 value here and we shall simply carry out swap operation on them. Just take a look at what happens in the list form. We had our 100 node, we divided by 2 and then we found out the value at index 2 and then we simply swap those two elements. And then we carried out this operation again. We divided 100 by 2 and found out index 1 to be our parent and then we swapped those two. Now, again, when we try to append 75 into our list, we shall first of all return the parent node for 75, which is located at 6 index. We shall divide 6 by 2 and then it will return 3. And then we get to know that 61 is the parent node of our 75 node. And then we shall compare 75 with 61. And based on that, we shall be carrying out a swap operation on these two. As you can see, 75 and 61 have been swapped. Now 75's parent is 100. We carry out floor division on it again, and then we find out the parent, and we see that 100 is actually greater than 75. So we shall not continue any other operation. We shall not be swapping these elements, as you can see here. Now again, when we were giving an explanation, we just shifted all the elements to the right. But when we carry out our actual operation, we shall be starting from index 0. Any doubts until here? I guess there are no doubts. Now we shall be taking a look at helper methods before we go into our insert code. These helper methods will make it much easier for us to carry out our insertion as well as removal operation. So as usual, we shall be defining our max heap class. And as I said, we shall be initializing our heap using a list, a regular list. Now we shall be having functions for returning left child and right child. So when we were having our all the elements shifted to the right, when we were not occupying index 0, we were simply returning 2 times index. That shall not be the case when index 0 is occupied. For example, if 100 is occupied at index 0, then if we want to find out the left child, then you shall simply return 2 times index plus 1 because it's located at index 1, as you can see here. And with right child, it will be return 2 times index plus 2. As you can see here. Now we want to return our parent as well. So for that also we shall be defining a function which will be index minus 1 upon 2. Now index minus 1 because when we were explaining we had shifted all the elements to the right. Now if you want to find out the parent element without any errors, we shall say index minus 1 upon 2 because index starts from 0. And we shall be carrying out floor division on it so that we'll properly get the parent index. And then we shall be defining a swap function which shall be taking two indices as its parameter, and then it shall carry out this swap operation on it. Did somebody notice something interesting about this swap operation? Just take a look at how it's implemented. Does anybody notice something about it which relates to the concept that we covered in our first class? I'll wait for 2 minutes. You can send a chat or unmute your mic. Does this remind you of a concept that we studied on our day one? Anybody has any idea? This swap function actually reminds us of the pointers concept that we studied about in our day one. We spoke about lists being mutable data types and integers being immutable data types. So, in a list is much easier to carry out this swap operation. If, on the other hand, these would have been indices on which, sorry, integers on which we have to carry out our swap operation, we would have to declare a temp variable and then we would have to carry out our swap operation, if you remember. But since lists are mutable, we can simply swap these elements by simply equating one to the other and vice versa. Is that clear? Now let's take a look at the code for our insert method. So insert shall be taking in a value parameter as we have already studied in our introduction how the logic will flow. 100 shall be at the last location and we shall essentially just append this 100 into our heap list using this function. And then we shall be declaring a current variable, and the current variable will be equal to the last index, and that last index will actually be length of the heap minus 1, because if the length is 5, then the last index will be index equal to 4. So this shall be our current variable, which essentially goes through the index of our new node that we have appended into our list. Now, as usual, we shall be carrying out comparisons of this value with its parent. So we shall be running a while loop here and we shall be changing the while condition here. We shall see what that condition would be soon. So first of all, we shall have to define our left child and right child. And we shall be carrying out our self operation on this current node on its parent, as you can see here. Just take a look at how we have written this. So swap function takes in the index as its parameters, as its input parameter. So current will be the index of the last element, the new element that we have added into our priority queue. And the other index will be the index of our parent, of our current node. And then, in order to continue to run this loop, we shall be updating the value of our current node. And then it shall become equal to this parent node. So essentially, when we declare current to be equal to self.parent current, again, we shall be able to go back to this node and we shall be able to assign the current value again to it instead of getting it changed to another value. That is the 72 value for this example. And then it shall carry out this operation until our heap condition is satisfied. So what is the heap condition? First of all, the current value should be greater than 0. If it reaches 0, then our loop will stop running. And also, we shall not just carry out this operation mindlessly without having any comparisons. So for that, we shall be having another condition, that is heap current element is greater than the parent of the heap. It might look like a complicated code, but just take a proper look at it and you'll understand. Heap element at the current node and it's compared with heap element at the parent location. Is that clear until now? So this is how our elements shall be rearranged after we append our new value into it. And then again, we added 75 into our heap as well. So these are all of our heap helper methods. And then this is our insert method. Now we shall be running our custom input. We shall be adding in these nodes into our heap. And then we shall insert, as you can see here, we shall be inserting 100 first, and then we shall be inserting 75. And these are our expected outputs. Here you can see. So at first, when we initialize our heap, we shall have 99, 72, 61, 58. And then when we append 100, when we insert 100 into our heap, we shall see that it is not at the end of our list. It has bubbled up to index 0, and rest of the elements have also been rearranged. 72 was right after 99, and now it's at the last location. Then afterwards, when we add our 75 value into our heap, you can see it has also bubbled up to its appropriate position. And as you can see, 58 was after 61, but now 61 is at the end of the list, and 51, 72, they have all been arranged like this. So this is what we expect our output to be after we run our insert code, and that's exactly what we find here. Does anybody have any doubts until now? We shall be talking about the removal operation. So, as heaps are revolving around priority queues concept, in our priority queue, the first element is the value with the highest priority. So, whenever we remove an element from our heap, we shall not give it any specific parameter. That is like we wouldn't say remove 50, 60, or anything. We shall simply say remove, and it will remove the element that's located at index 0, which means the first element of our heap. And then we shall be carrying out a sync down operation on our heap, and then we will rearrange our heap to satisfy the heap property. So what will essentially happen is that we will get rid of our 95 value here, and then as you can see, it's no longer a proper heap. So, so in order to protect our heap, we shall simply take the last value in our heap. We shall take this 65 node in this specific example, and then we'll add it to our parent. We shall keep it at index 0. And as you can see, our tree is still complete. And then after that, we shall be carrying out the sync down operation, which means we shall be checking out if the max heap property is satisfied. And after that, after the condition is satisfied, we shall stop running our code and we shall be removing the node. As you can see, 65 was compared with 75 and 80, and then it was swapped with 80, and then it was compared with its left child 60, and since it's greater than 60, we didn't carry out any swap operation. So let's take a look at this priority queue that we can see here. Now we shall be defining our remove function. As you can see, it doesn't take in any value parameter. Now we shall be running some exceptional condition. For example, if our heap does not exist, then we shall return none. If length of heap is 0, then return none. And if length of heap is 1, then we shall simply return self.pop, which shall return the single element that was existing in our heap. Now take a proper look at what we are doing here. So in order to carry out our remove operation, we shall be using the help of a variable. We shall be declaring a max value variable here, and this max value variable will be equal to the index, the value at index 0, which shall be heap 0. And after that, we shall have to get rid of the element that's at index 0. For that, we'll be doing something really interesting. Just take a proper look here. Heap 0 will be equal to self.heap.pop. We shall see here. As you can see, we simply took the element that was at the last location and we equated it to the location at index 0. As you can see here, and we simply replace the value of 80 with 60 by this one code line. Any doubts in this line? And then we shall carry out our next operations here. We shall be calling our sync down method here, because right after we take the last element from our heap and replace it with the element at index 0, you shall have a heap that does not satisfy the heap property, and you shall have to rearrange it. And for that particular task, we have defined a new function, which is the sync down function. And the sync down function by default will be taking in this 0 value as its parameter, which means the sync down operation will be carried out at the element at index 0. And then we shall return the value that has been popped from our heap. Now we shall be taking a look at our sync down method here. As you can see in this example, we got rid of our 95 node, and then we took the last node in our heap and we replaced it with that location. And then we are going to carry out our sync down method on it. So in sync down, we simply compare it with simply compare the value at index 0 to its children, and then we keep on swapping them. Now we shall be defining our sync down method. So this is our sync down method. It shall be taking in a value parameter. Now, in order to help make this code, we shall be taking in a max index variable and we shall be equating it to our index. And then we shall be running our while loop until our condition is not true anymore. So in this case, we shall have to initialize a left index, which means the left child and the right child. As you can see here, left index will be equal to the left child function that we had defined in our helper methods. If you remember, just now we did it. And then right index will be equal to the index of the right child of your index. As you can see, we have passed in the index parameter. This is our index 65, and left index will be the index of this left child. As you can see, it shall be returning the index. Now we shall be carrying out comparisons of the children along with this max index here. As you can see, firstly, we shall be comparing left index with our max index, and we find out that it is equal to that it is greater than max index. So we shall be carrying out a simple code line on it, which is we shall simply declare max index to be equal to the left index. So in our case, we have firstly done that. And again, we have another code line, which is essentially the same operation, just on the right index. We shall be running the same code lines for our right index as well. So in our case, as you can see, max index has now been set to 75. and 80, which is the right child of 65, is actually greater than 75. So we change the value. Okay, so as you can see, 80 has a greater value than our initial max index, which was 75. And then we simply declare max index to be equal to this 80 value here. And then now, as you can see, the value of max index has changed. It's no longer this 65 over here. So if that's the case, we shall be carrying out our swap operation with max index and index. As you can see, the value of 80 has changed and it has moved up in our heap. And now our index is still the same. And then we shall carry out the same operation again and again until the heap condition is satisfied. Now let's take a look at a special case here. We are defining left index and right index. But for this case, you can see that there is no right child at all for 65 index here. So if that's the case, then there's no point in running this code. So for that, we shall be adding a conditional to our left child and right child code lines, which shall be this. If left index is less than the length of our heap, and if right child is less than the length of our heap, then we shall be running this left index and right index code. Otherwise, our code shall not run. As you can see, if right index is less than the length of our heap, so for example, if the right index here is 6, for example, but there is no nothing at this 6 location, so our code wouldn't run in that case. Comparison wouldn't go on here. For 65, the left child is 50, which is at location 5. And the length of our priority queue, our heap, is equal to 6. And the location of 5, this 5 is less than 6. So our left index operation shall be run. But our right child operation shall not be run because there is no right child for 65. As you can see, we have added these new conditionals to our code. If anybody has any doubts until now, they can unmute their mic. And this if condition.
Sorry, I was having a like technical glitch. Can you just tell me what you have taught? Like the index max value. I wasn't able to hear for that part.
Okay. So do you want me to take it from the starting?
No, just for the past 1 minute what you were speaking. That's it.
Okay, this condition if max index or are you talking about this right index less than length of
Yeah,
heap?
from if right index is less than length self taught here.
Okay. If, for example, your node, this index does not have a right child or a left child, then there's no point in assigning max index to your child. So for that, we shall be adding in additional conditions, which is the right index, which is a number, the location of our right child. If it's less than the length of your heap, then only this code will run. Let's bring up our queue, then we can understand it. Um, so let's take an example of the left child for our 65 node here. 50 is located at index 5 and the length of our heap is equal to 6. Now 5 is less than 6. So we can run this code line. But say, since 65 does not have a right child, there shall be no max index variable declaration happening for our right child. So that code line shall not be run. This same code that we have written for right index will be written for our left index as well. Is that clear?
Yeah, got it.
Okay. So now let's take our custom input and run our removal operation. So this was our sync down code. And yeah, we have written is this if conditional where this swapping function will be carried out if the max index is no longer equal to the initial index that we have assigned here, which means we found out that the node that we had initially assigned at value 0 was not in fact the max value. So we found out that somewhere else a max index element was there.
All candidate keys are called
Okay. Otherwise, if max index is still equal to index, then we shall simply return and our while loop will terminate. As you can see here, now we have our sync down method and we have passed in value 0 parameter to it. And now we shall be running our code for this custom input here. We shall be getting rid of our 95 node. And then we took our 80 nodes and we added it as index 0. And then we got rid of 80 as well again. And then again we changed the index 0. And then we carried out our sync down method on it. And then we satisfied the heap condition. As you can see here, this is our remove method. And then we inserted the following values into our heap. And then we carried out the remove operation 2 times. So let's see what happens here. First, we inserted all these values into our heap, and then we popped off the first element, which is 95. And then after that, you can see all of these values have rearranged themselves. As you can see, 80 is now the value at index 0. And then after that, we shall carry out our remove operation one more time. And then 75 will have become the max index. And as you can see, all the elements have rearranged themselves 60, 65, 55, and 50. So this was it for heaps. Now we shall be studying about the recursion uh, concept. And everybody has already learned about recursion. We shall have a recap of it. So recursion is a concept where a function keeps calling itself until it doesn't. And when does it stop calling itself? When a base case is reached. So let's take an example for this. We will define a function.
चैट चैट ऐप पे यही है हाँ क्विज का लिंक आएगा क्या
So we shall be defining our open gift box function here. And our base case for our open gift box function would be to return a ball if there is a ball found in our gift box. So we shall continue to run this open gift box function until we find the gift box. So what can happen is you open the gift box and you find another gift box. So you keep on opening the box until you find the ball and you return the ball, and then the function stops, it terminates on itself. So if ball and return ball, these two code lines are actually our base case, our termination case. If we don't have this termination case, then our open gift box function will continue to run infinitely until stack overflows. So yeah, a few things to keep in mind about this recursion concept is that the same process keeps repeating. So the process of opening the box will be the same. There would be no difference in it. And as we keep on recursing, which means if we keep on calling the function on itself, the problem actually keeps getting smaller and smaller, and we keep getting closer to our solution. So this is essentially how our function works. We kept on opening the box until we found out the ball and we returned the ball. This was our base case. There's no need to go deeper into this. Now we shall be talking about this call stack concept. If you guys remember when I spoke about stacks and queues, I said that we shall be studying about the call stack concept as well. Call stack is how Python actually runs our functions. It's very interesting. Let's take a look at it. Let's define a function called function1, and it will simply print 1. So after we call this function, it shall be added into it will be pushed into our stack. And now we are doing something interesting. We are calling another function, function2. Let's define it. So function2 simply returns 2, the string 2. And function2 also does something interesting. It returns function3, which means it calls on function3, and function3 simply prints out the string 3. So as you can see, if we want to carry out all these 3 operations, we shall have to simply call this function1. Let's take a look at it in our console. As you can see, we call function1. And then this is actually VS Code, where you have this option of running and debugging. And then when we go into call stack, just a minute. Okay. So as you can see, this call stack option here, we debug console. And as we go step by step into our code, this is actually similar to the Python tutor website that I showed earlier. It visualizes the code lines one by one for you. And here you can see we have run function1. Now let's see what happens. After we run function1, we have pushed it onto our stack. And after we push function1 onto our stack, the function will start running. And after that, you can see that function2 will also get pushed onto the stack. And then after function2 is pushed onto the stack, it will start running. And then when it starts running, you can see the first line is function3. Then function3 will run, and it will simply print out this 3 string here. As you can see here, function1 has been pushed onto our stack. And then after that, function2 has been pushed onto our stack. It starts running. And when it starts running, function3 is called. And when function3 starts running, this string 3 is printed over here. After that, function2 has finished executing this function3 code. So it shall be returning 2. It shall return this string 2. And then again, function1 will have finished executing this function2, and then it will be printing out 1. So this is how we are understanding the concept of call stack. Okay. Now I would actually like to make this recursion concept easier. So for that, I shall be using a very relevant and relatable example. Yeah, this is our simp function, which makes this person keeping on bothering you all the time. So let's take a look at the lines, code lines here. So the brain of the simp tells the person to ask you a question. They ask you whether you will go out with them, and our answer can either be to reject or to accept. Either you can accept or reject, or you can say yes or no. There are no other possibilities. So since this is a simp, they shall be running in a different way. If your answer is reject or your answer is no, their brain will simply, instead of saying understandable, have a great day, they'll say, oh, you're playing hard to get, I see. And they will try again, they will try to ask you again until you finally say yes. I don't know if that will exactly happen or not, but this person wouldn't stop bothering you until you finally say yes. Let's see how this recursion concept will be carried out endlessly. So this person asks you the question whether we'll go out with them or not. If we reject the person, they say, you're playing hard to get. I see. Now again, I say no. Again, it keeps asking me the same question. And if we say yes, then it will stop. Then our function will stop working. I think this concept, this example would make the concept easier for you to understand. I wrote this code by myself actually, and I just came up with it at 7 p.m. just right now, just some time ago.